Hello class, so here we are with lesson 2. We're going to explore several other really important ideas as they relate to function and function behavior in this lesson. So the first thing we're going to talk about is the concept of average rate of change. To do that, we're going to look at sort of an application setting here, and that is a new car is valued at $28,000. It loses $1,750 in value each year after it is purchased. Let T represent the number of years since purchase and F of T represent the total value of the car. Just in a simple brute force way, the way to go about this would be after 1 year, we would subtract 1 year's worth of devaluation. So it would be 28,000 minus 1750. So that would be 26,250. And then after 3 years, we would subtract 3 times 1750 subtracted from 28,000. That would be 22,750. And then after 7 years, 7 times 1750 per year subtracted from 28,000 leaves 15,750. And then after 12 years, 12 times 1750 per year subtracted from 28,000 leaves a value for the car of 7,000. And then finally after 15 years, 15 times 1750 subtracted from 28,000 would leave $1,750. So now average rate of change. So here is the definition that we're going to be using throughout for this. Average rate of change of in this case, we're going to go from t equals 1 year to t equals 3. There's a specific way of setting this up. It's, of course, the ratio of change of output to change in input over the corresponding period. And the unit will be a rate unit. It'll be a fractional unit when we're done. So what is change of output? Well, it's the function evaluated at year 3, that's our ending year, minus the function evaluated at year 1, that's our starting year, over year 3 minus year 1. And so that ends up equaling the output at 3, which is 22,750, minus the output at 1, which is 26,250, all over 2. And when you do that calculation, you get negative 3,500 divided by 2, which is negative 1,750, and there needs to be units. Dollars on top and years on the bottom, dollars per year. So that is the average rate of change of this depreciation model over years 1 through 3. Now we're going to do the same calculation from the table over years 7 to 15. So I'm going to use the initials now, AROC, for average rate of change, and this would be from t equals 7 to t equals 15. So that's going to be the output at 15 years minus the output at 7 years over 15 years minus 7 years. So from the table, that's 1750 after 15 years minus 15,750 at 7 years divided by 8. So that's negative 14,000 divided by 8. Doing the math, you get negative $1,750 per year. Something special is happening here. For any interval we would pick on this depreciation table, when we compute average rate of change on that interval, it's going to be the same. And that leads us to an important conclusion about the relationship between the average rate of change of a function and the nature of that function in this special case. What can you say about the average rate of change between any 2 points in this situation? And so AROCs are constant. So the relationship between input and output is linear. That's the special case here. Later we'll learn that that AROC in this one special case where they're constant morphs into the constant value for slope in the model. We're actually going to use it right here. Those AROCs are going to become the slope in this model equation right here. So now let's write that model. Of course, the B value is the value at time 0, so that's going to be the 28,000. So this is f of t, the value of the car, equals negative 1750, the average rate of change, or slope, times time, plus 28,000. So that is our formulaic relationship between f of t and t. And then it asks us for practical meaning, so we need a couple of meaning sentences here. So a slope of negative 1750 means that the car's value decreases $1,750 per year. And we need a period at the end. It's an actual sentence. And then a vertical intercept, because the y-intercept is the vertical intercept, of 0.28,000, because it is an ordered pair, means the car's value when new is $28,000. And again, a period at the end. And then finally, we're going to look at the case where the f of t value equals 0. What that really means is the output is 0. So that means that we're talking about the time it takes for it to reach $0. So we take our equation in this situation right here, take this equation, and replace f of t with 0. So 0 equals negative 1750t plus 28,000. And remember that when you have an expression where you have an input variable, in this case t, and you're trying to find the value of that input variable by working backwards from the output it produced, you're actually undoing a PEMDAS process. PEMDAS is the order of operations. So when you're undoing, you're going in reverse order. So what you did last in the evaluation process, when you had an input to get an output, what you did last was add. So that's what we have to undo first. So we have to undo the add 28,000 by subtracting 28,000. So that gives us negative 28,000 equals negative 1750t, because obviously these are opposites. And now we're going to undo the multiplication by negative 1750. So to undo that multiplication, we divide both sides by negative 1750 to undo multiplication. And a negative divided by a negative is positive, which is important here. So we get a positive 16, and actually the units for that is years. So now we have to do this part. We have to interpret your answer in the context of the problem. That's really an important aspect of this. So put it in a meaning sentence. So after 16 years, the car's value decreases to $0. So that's the average rate of change. And we'll be coming back to this when we talk about other types of function behaviors in a little bit. So let's move forward here. We're actually going to go to the next part of this lesson 2 activity, activity 2. So here we're going to be actually using an example function to look at something that isn't just strictly increasing nor strictly decreasing, but has an interval over which it's decreasing, has an interval over which it's increasing, and therefore it passes through either a bottom or a top in terms of the y values for the function. And so we get to talk about the nature of functions when they have those behaviors going on. So we're just going to use a simple second power function here. And the best way to handle this right now is just simply to graph it on a grapher. So I'm going to actually pause this for just a second. So now I have the TI-84 up here on a simulator, so it's working just like it would work for you. And so we're going to go to Y1 and we're going to graph this second power equation. So I'm going to enter 3, parentheses open, x plus 1, parentheses close, squared, subtract 4. And I'm going to view the graph of this in the standard window. So that's just a zoom 6. Zoom is up here, and then 6. And there is our graph. Let's find the important features on this graph and then transfer them to the activity. So definitely there are some things here that are important. For instance, this part of the graph is where the y values are decreasing as x values increase. That's the interval over which this graph is, this function is decreasing and the graph is decreasing. And then this part is where it's increasing. So at this point right here, we're passing through a minimum. And in this case, it's what we call an absolute minimum. So, so then we're going to identify that with the calculator. So what I'm going to do is go to the calc menu, second calc, and I'm going to choose number 3 for minimum. And then the little spider is blinking there, and so what we want to do is we want to arrow slightly to the left of the perceived minimum, anywhere to the left, and press enter, and then slightly to the right of the perceived minimum, and then press enter, and then press enter for our guess. And clearly, even though the calculator is approximating it, that minimum point is -1, -4. Also, the symmetry is obvious here. This graph seems to fold across itself in such a way that the vertical line passing through that point is what we call the axis of symmetry. So we'll actually identify that as x equals -1 for our axis of symmetry. And then the last few items that we need to get all the intercepts, because again, those are important features of the graph. Where does it cross through the x and y axes? And so we need to determine where that passes through the x and y axes. And so I'm going to use the tool. So I'm going to go here, second calc, and I'm going to use the 0 command. And so this time we want to move the spider to the left of the perceived 0. See, it says left bound. And so I'm going to arrow to the left and above the x-axis over here, anywhere, press enter, and then the right bound. So I'm going to arrow below and to the right, anywhere, and then enter for my guess. We'll round it to 1 decimal place, -2.2, 0. So this intercept right here is -2.2, 0. All right, so we're going to repeat this for the other one. So second calc, and again 0, enter. And this time we're going to arrow over close to, but below and to the left of the x-axis on the right side. That's our left bound, and then arrow to the right and above. That's our right bound, and then enter for our guess. And again, to 1 decimal point, that's going to be 0.2, 0. And then the vertical intercept is found by using the value command. So you go to second trace value, and then it lets you type in a value for x, and we want the value when x is 0. That's when we're on the vertical axis. And so then y is -1. So then this is 0, -1. So really, a lot of stuff's going on here. We're identifying the interval over which it decreases. So it decreases on -infinity up to, but not including -1. And it increases on not including 1 up to infinity. Then it has that absolute minimum. Absolute means there's no other y value smaller than this y value. For this particular type of graph, that's going to be the case. And then we have all the intercepts, the x and y intercepts. That's typically the kind of complete graph that you want to portray. So now we're ready to take all this information and go back to our activity. So let's do that. Let's switch back over to our activity. So I'm going to portray all of this information now. So let's go ahead and do our absolute minimum at -1, -4, and label that. Let's do our x-intercept at -2.20 and 0.20, and our y-intercept at 0, -1. Let's draw our vertical axis of symmetry for this graph, that vertical folding line that the graph seems to fold across symmetrically. And now, with all of this information, we should be able to draw a symmetric graph freehand, sort of like I've talked about before, Bob Ross and the painting show, forget what they call it, but it's on Saturday mornings. He's done it for years, and he is so gentle and just the serenity in his painting style. You want to draw a happy little graph, just like he draws his happy little clouds. So here's the happy little graph that we're going to draw for this. So then we want to go ahead and put our information about the decreases on what interval, decreases on -infinity up to, but not including -1. Then it increases on not including 1 up to infinity. Some other things, we've written all of our intercepts as ordered pairs. They call this graph for a squared graph like this, x to the second power. It's called a parabola. And then we want to describe this absolute minimum. And it's the point -1, -4. So that touches a lot of bases in lesson 2 on just general function behavior, more complex than linear behavior. All right, now we're going to look at the nature of increase and decrease. And actually, we only got 2 examples here. We'll come back to them. I'm going to go to a blank page right now, and I'm going to develop basically the 6 different ways that behaviors either increase or decrease, graphical behaviors, function behaviors, and then talk about the nature of average rate of change with those. So I'm going to pick a blank page here for right now. And I'm going to create some basic graphs here. I'm going to create an XY in the first quadrant here, an XY in the first quadrant here, and an XY in the first quadrant here. I'm going to do count to 4 and then count to 4. And I'm going to count to 4 and count to 4. And then count to 4, and then count to 4. It's just an example of these behaviors. There are many ways that these behaviors show up, but these are easy examples. So this will go to 4, and it will start at 0. This starts at 0. This goes to 4, 0, 0, 4, 4, 0, 0, 4, 4. I'm going to portray the only three basic ways we can increase. So our goal, we're going to start at 0. Actually, let's use a different color here. We're going to start at 0, and our goal is to end up at 4, 4. So we're going to start at 0, 0, and end up at 4, 4. And all three of these, start at 0, 0, end at 4, 4. Obviously, to do that, as we move from left to right, we're going to have to increase. So these are all increasing scenarios. The first one is the most basic that we studied the most about, and that is to increase so that the average rate of change is constant, to increase at a constant rate. That is a linear model. And then the average rate of change over this entire interval, as we learned earlier, they're constant. And in this case, it's easy to see that the change would be the AROC between the endpoints would be 4 minus 0 over 4 minus 0, which is 1. Now, we're going to, in the second scenario, we're going to increase slowly, then speed up our increase. So in the first half of our journey, we're going to increase very slowly. So we're not going to go halfway, we're only going to go a quarter of the way. So by the time we've gone halfway in X, we've only gone a quarter of the way in Y. And then we're going to make up all that in the second half. So it's going to look something like this. And this point right here is now 2, 1. So and I'm going to attempt to draw it as a gentle curve, not as two line segments, but as a gentle curve. And so now we can't generalize about the average rate of change. It's not the same all the way through. So we're going to break it down into two subintervals. We're going to draw the secant line from 0, 0 to 2, 1, and then we're going to draw the secant line from 2, 1 to 4, 4. And now we're going to talk about the average rates of change for those two. So this one is going to be 2 minus 0 over, 1 minus 0, excuse me, I used the y value. 1 minus 0 over 2 minus 0, or 1/2. So this is the first AROC. We'll call it AROC 1, is 1/2. So this is 1/2, this AROC. And now this AROC is going to be, we're going to end at 4, 4 here, so it's going to be 4 minus 1 over 4 minus 2. And that's going to be 3/4. So this is our second average rate of change. Call it average rate of change 2. So the 1/2 is smaller than the 3/4. So the AROCs are not remaining constant as X increases, they're increasing. So AROCs are increasing. They're getting more positive. Now, let's look at this last scenario. The last scenario, we're going to increase rapidly at first, then slow down our increase. So that means in the first half of our interval from 0 to 4, we're going to do most of our increase. So we're going to go from 0, 0 all the way to 2, 3. So write that right here. Here is 2, 3. And of course, this is 4, 4. And so we're going to do it in a smooth curve way, so it's going to look like this. And so again, the AROCs we can't generalize about. They're not remaining the same. So let's do the secant lines. So let's do the secant line from 0, 0 to 2, 3, and the secant line from 2, 3 to 4, 4. Now let's compute this average rate of change. We'll call it AROC 1. And so that's going to be 3 minus 0 over 2 minus 0. And so that is going to be 3/2. Whoops. You know what? I realized something. This is not 3/4, it's 3/2. So it's much larger. Let me fix that. 3/2. But again, same idea. This is definitely bigger. That AROC is bigger than the first one. And so then the second AROC up here, this one is actually only 4 minus 3 over 4 minus 2. So that's 1/2. 1/2. I'm going to get that in there, 1/2. And so that's our arrow C2. And so definitely this first arrow C, oops, undo that real quick. This first arrow C is much larger than the second. And so in this case, arrow C's are decreasing. They're becoming less positive. To become less positive is to become more negative. So you kind of have to look at it that way. Becoming less positive is becoming more negative. So these are the three basic ways that things can increase in terms of single monotonic behavior. Of course, you know, ultimately you can concatenate and connect these different basic nature types of increases together and get more complicated increases. But right now we're just looking at the basic ones. All right, so I'm going to scroll down and we're going to do the three ways we can decrease. Extend the page a little bit. So now we need to draw x, y's so that the y's are below. And so again, I'm going to go 4 and then 2, 1, 1, and then 0. So 0 to 4. And then -4, -2. And -4, -2. Of course, this is 0. And 0, and 0, and 4, and 2. And then again, 0, and 0, and 4, and 2, and -4, and -2. Now we're going to talk about the three basic ways of decreasing. And our goal in all these cases is, again, we're going to start at 0, 0, and then we're going to end at 4, -4, which obviously means that as we move from left to right, the y values are getting smaller, we're decreasing. So the first one is decreasing at a constant rate. Of course, that's linear decrease. And as we said before, the arrow C's are constant. In this case, if we did the computation, it would be -4 minus 0 over 4 minus 0, and that's -1. But the important thing for linear decrease is that the arrow C's are constant. So now our goal is still for -4 here. And we're starting at 0, 0, but now we're going to decrease rapidly in our first part of our interval and then decrease more slowly in the second part. So as we go from 0 to 2 to the right, we're going to do most of our decrease. So we're going to drop all the way to -3. So this is going to be 2, -3, and then the rest is a much smaller. So now we're going to do our smooth curve. There's our smooth curve modeling this type of decrease. Now we're going to draw our secant lines in. And obviously, arrow C's are not constant. So this definitely looks steeper negative. Let's compute it. So it's, let's do -3 minus 0 over 2 minus 0, so -3/2. That's that arrow C. And then this arrow C is -4 minus a -3 over 4 minus 2, so that's -1/2. So definitely this is more negative than this. Oops. I'm supposed to do that. Get it back. There we go. So yeah, the -3/2 is more negative than the -1/2. So in this model, the arrow C's are becoming less negative, so they're increasing. So arrow C's are increasing because they're becoming less negative, which means they're becoming more positive. So arrow C's are increasing. So now, scrolling back up, the last way to decrease. And that would be to, again, our goal here is for -4, starting at 0, 0, but would be to decrease slowly at first and then more rapidly later. So in the first half of our journey, we're only going to decrease to here. we're only going to decrease to -1. And then the second half, we're going to make all that up. So again, here's our smooth curve. Okay, and now we'll draw our AROCs in, secant line, and of course they seem to be becoming more steep negative, but let's compute this one. This one's going to be -1 minus 0 over 2 minus 0, so that's -1/2, and then this one is going to be -4 minus a -1 over 4 minus 2, and that's -3/2, and certainly -3/2 is more negative than -1/2. So in this case, AROCs are decreasing, clearly. So what's interesting in summary here, before we wrap things up, is that we have two scenarios that have something in common, where AROCs are decreasing. And so let's look at both those scenarios. They're in this far column here. So there's the one, this one, where we're decreasing at an increasing rate, if you will. AROCs are decreasing. And then if I look right above it, there's also this one, where we're increasing at a decreasing rate. So if we're increasing at a decreasing rate, or if we're decreasing at an increasing rate, we have the same behavior for the average rates of change. They're decreasing. So if we put those together, we create a type of what we call concavity. I'll show that right down here. So if you tie the increasing at a decreasing rate to the decreasing at an increasing rate, this whole region, anytime you have any or all of this behavior, is called concave down. It's like a bowl that's flipped over and spilling water. And then the two scenarios that tie together for increasing AROCs, and I'll go ahead and change the color of my highlighter to make this stand out a little differently. It's the bottom one where we were decreasing at a decreasing rate, this one right here, and the one above it where we were increasing at an increasing rate, this one. And so if we put those together, end to end, we get this. We get decreasing at a decreasing rate and then increasing at an increasing. If you have any or all of this behavior, you have what's called concave up behavior. And so now we should be able to finish our activity. So let's go back to our activity here, and let's scroll down. And so what kind of concavity do we have? Well, on the left, we've got something that's decreasing, but it's decreasing rapidly at first, then slowing down as decreasing. This is decreasing at a decreasing rate. It's part of a concave up bowl. This is part of a concave up shape. And so, of course, we'll use the initial CU for concave up. And the average rate of change on concave up are increasing. What kind of concavity is the one on the right? Well, it's increasing at a decreasing rate. It's like a part of a bowl flipped upside down. So this is concave down. And so this is CD, concave down, and the average rates of change here are decreasing. Very important idea.